Okay. So it looks like we're live. Give me a second to set up the things. Where's the link for this? Let's get back to the power. You guys can sit on the first slide for a second. There we go. There we go. Okay, so let's start, right? Welcome. Let me clear screen up so I can see what's happening here. So today we have the Opal Kelly Artix UltraScale Plus board. This is kind of Xilinx's official dev board. Normally they develop a dev board, but this time Opal Kelly has developed a dev board. So I had just received it in the mail today, so we're going to go through it and play around, look at some of the documentation, do some of their examples, and get it working in Vivado. And that's our goal and plan for the next hour. Hopefully we can finish everything. So we'll go through the product slide in a few seconds. Well, let's go through agenda. We're gonna go through the product slide deck to see what Opal Kelly is advertising. Talk a little bit about Opal Kelly support and documentation and forums and other ways. Then we're gonna talk about some of the hardware software, my hardware software opinions that I'm like, I'm not sure what I would think of this or whatnot. Then we have some ideas, some new Syzygy add-on boards. Then we're going to go through Opal Kelly's front panel, go through their examples, do a Vivado board file example, and then kind of do a quick thing into what future projects I would like to look into. So let's go ahead and look at the slide deck that's going to be here. So this board, when it comes to peripheral, like the base peripheral, are pretty simple, right? So it says USB micro. It's actually USB-C. I don't know why they say USB micro there. USB-C. So basically, you have flash, you have DD, SRAM. You can see you have some SMA cables for one transceiver, and then you have dual SFP for some other transceivers. But overall, there's not a lot of peripherals built into the device. You have to use their Syzygy. I hope that's how you say it, right? Syzygy ports right here. And if you do notice, the transceiver ones on the top right here are slightly larger. They have slightly larger pins for where those ports are connected. This is the biggest of the Artix UltraScale Plus family, the 25P. There's, was it 10, 15, 20, 25P? The 10 and the 15 come in the smaller form factor, and that's kind of what I would like to look into the long run, but that's not available at the moment. Yeah, this is kind of what we talked about. 2 SFP, plus, that's good. Got some clocks, that's great. Flash, DDR, and their host interface they don't really talk about. But yeah, let's go through it. So the front panel, they have this really cool software that allows you to interact with their USB-C host interface. We'll go through more of that later. It's good performance. Yeah, we tested that. This is so far it seems really nice. I kind of want to look at it and see how hard it is to get up and running for my own custom designs. But for their examples, looking through the the different code they provide, there's a lot of ways you can integrate your own software into their platform. They provide you with low-level Python, C++, C#, MATLAB, LabVIEW. We'll have to look at their API section, see what they have going there. Yeah, kind of building off of that right here. Here's what you can do. Java as well and JavaScript. Yeah, all this stuff they have really good examples about how to get this up and running. And I'm gonna look through probably the Python is what I'm gonna lean on the most. Maybe some C# GUIs inside of Visual Studio. Oh, these are the JSON features. So yeah, you can create these little counters using XML based graphics. I gotta figure out, they've got to have a tutorial about how to do all these fun little things, but it'll be fun to look at. So the syzygy overview, this is kind of like an open source or open standard, an open standard for connectors. It's kind of a middle point between PMOD, which is kind of your low speed 8-pin data ports, and then the FMC over here, which is kind of a high pin count, and then this kind of fits in the middle. So let's see where we go from here. These are the peripherals that are currently available for this board. I got 2 breakout standards and 2 breakout transceivers. You can see that my breakout standard is currently connected to the board. There. I ordered transceivers, but they sent the test cards instead. But I already communicated back with them, so that'll be coming back soon. I want the digital PMODs. I have a bunch of PMODs already. Ethernet would be useful. PCIe Express would be useful. The camera would be fun to play around with. Maybe the multi-sensor. But yeah, I would like to look into these different transceivers. I have a few ideas. Later, I have a page full of different ideas to explore. Do they have reference designs? ADC, Ethernet designs. This looks cool. I really want to try this out and maybe even do from one board to the other. Just get this cable right. Just get one of these cables that go from one board to another. And just play around with root on one and endpoint on the other. Maybe try to get some DMA going. Some PCIe based DMA. And there's the price, the availability. The shipping date's actually correct. Oh, this is the 830. This is the SOM 83010. So this is the same FPGA just as the SOM. They give you more DDR, wider interface, more IO, but basically the same. Okay, cool. So those were the slide deck for the product slide. So let's talk a little bit about the support. So far my interaction with Opal Kelly has been great. They're not sponsoring this, but so far they've been very supportive of communication with sales and technical support. They have active forum pages where you can log on and be able to make posts and search other posts. Their website documentation is very good compared to other websites. They have a kind of a user login pin out website that gives you the pinouts, the schematic, example bit files, and the API software for the front panel. And then the FrontPanel API so far has been very impressive for what I've seen. Okay, let's see. So let's talk a little bit about what I would have liked to see a little bit differently with a board. So there's no buttons or switches. It would be nice for a hardware reset, but through the USB interface you can, you could do a hardware reset through that, which is possible. But a lot of times, you would like a button that's a hard reset, or some dip switches for some specific settings or something like that. There's no dip switches or push buttons on this board, and it's not a bad thing. I mean, maybe you could figure out one on one of these breakout cards or the PMODs or whatever. Not terrible, but it's a simple thing that might have been nice. Also, this board, let's go ahead and present our view to see if that's any better. This board is a little bit expensive for a hobby board, but that's saying that the FPGA by itself is about $500, right? So if I went to Avnet or DigiKey and tried to buy the FPGA by itself, it's almost $500. And this board is similar price to other professional Xilinx dev boards. So this is a professional Xilinx dev board and not really, I would say, a hobby board. Has some really cool stuff, but its price point, I think, is a little above a hobby board at this moment. Another feature I thought was missing, there's no JTAG over USB-C. First off, the USB host interface is not in the schematic, including like the configuration banks for the FPGA. I don't know how the mode pins are done. I think they're using select map to program the device from the USB hosts, but that's not in the schematics. So I don't know. And the USB-C also isn't doing power. It'd be really cool if we could also do power over the USB-C, but in the documentation it doesn't say, and I haven't really tried to do the power over USB-C. That being said, I do have a future project where I'm gonna show how you can do a custom Xilinx virtual cable over the USB-C interface into the internal JTAG primitives. That's something I want to look at. DDR interface. For this price, I would expect a higher capacity. I mean, I think you could just upgrade the part to a higher capacity, still have the same pin out. So a little sad about that capacity. I would like it to be increased. A SODIMM would have been great, but there's probably, they almost have every single pin, all the FPGA pins mapped to something. It would almost be impossible to get a SODIMM. A SODIMM, you'd probably be like, you would need probably 90 plus pins, and that would clobber a lot of your current interfaces. So I understand why they didn't do that. Parity. So DDR4 has a feature for address command parity, and I've been using this a lot in my personal research, and they just grounded it. I kind of wish that they didn't ground the parity on this board. I would have liked it being connected to the FPGA so I can use that for some DDR reliability testing. I would really like the parity connected directly to the FPGA. So those are kind of my hardware software concerns. Overall, they're pretty minimal. I am much more happy with the board than any negative opinion, and we'll go through some of the cool examples next. So here are some of the ideas. Real quick, right? Move these over. So some of the ideas that I would like to see as some synergy peripherals. I personally want to try to get a USB 20 gigabit transceiver working on this board. So that's more of my personal project, but I also like to see this 4K display port, maybe 8K, but 4K display port, 4K HDMI, an M.2 PCIe kind of endpoint module where you could stick like a hard drive or some other M.2 PCIe connection, or maybe just a full width PCIe connector that you could put on it. But it's more of a route to the endpoint. The PCIe connector they have is kind of connecting your endpoint to some other route. I would like to see kind of the other direction. A high rate analog oscope would be nice. Maybe some additional memory, but looking at the pinout and the timing issues and the trace lengths, I don't think that's really possible. A digital oscope would be great, something that has like an input clock and you could use the pins. I mean, in all honesty, that wouldn't be that hard to create, but it'd be nice if there's you could create some voltage, some different voltage levels and stuff like that on the expansion card. Wi-Fi, maybe an ESP32 would be a simple one to do, but I mean, if we can do an Arduino header and a Raspberry Pi header, there's all that expands your library by quite a bit. So those are my ideas. I don't know if they're going to make any, but I'll maybe send it to them because I would like to see it. Okay. So here, so let's go look at the Opal Kelly front panel. So I'm going to turn this guy on, and we're going to open up the front panel, and I'm going to show you some of the features. Okay, so let's go open up the front panel. Okay, so here's the front panel. This is what comes up. It automatically detected the 8320. Preferences, is there anything worth going? Computer before FPGA download. Yeah, so that's about it. So here you can load up little projects, and we'll load those up for the samples. These are little, these are their like XML based GUIs. Then you can load up bit files that we have right here. You can also look at some of the system configurations. Well, this takes a a minute or two to open up. But this has a few things. Also, Andres, thanks for the comment. Yeah, this FPGA looks really cool, and I'll show you some of the fun features. So this is the firmware. I checked the firmware is up to date, but here's some of the cool configurations. So it's like, oh, using the kind of the Syzygy open standard, we have little memories on each of them that tell us what board is attached. So we know that we have the breakout standard and another breakout standard, product version, serial number, port status. I don't really know what that means, but that's what we have for there. And then here we can program the system flash, which is connected to the USB host controller. There's a space for user memory. Let's go, I'll show you that in the documentation real quick. So if we go here to the documentation, remember, do they have the little picture? So right here we have a system flash and an FPGA flash. If we go to flash memory, this feature right here, system flash, programs what's connected to the USB host. And then we have FPGA flash, which is what is used to program the FPGA on boot up. And you just go to target, change it to FPGA flash, say configuration memory, and you can program it. So that's kind of the little front panel GUI. It's very simple at the moment, but let's go through some of their examples. So we got a few examples we're gonna go through. Some of them are gonna be the it's not JSON, it's XML file. It's XML. So let's explain how we get each of these running. So we downloaded all the bit files from the pinout website. So right here. So we download all the pinouts from the pinout website. So we can go ahead and download first bit into it, and it did it really fast. So I think they're using select map. That speed does not look like JTAG. That speed looks like select map. We have our temperatures and voltages. I really like this. We can see what our current on our FPGA is, and our core voltage. So we're doing very low right now with this little sample. So now if we load up so this is, under the Opal Kelly, we go here and we load up the XML. We have this little simple XML right here. There we go. So if you notice, can you see there's a little red LED right here under the fan, and this turns on the different LEDs. So I can turn on the LEDs, I can turn off the LEDs. There's only 6, so only the bottom 6 work. These don't have anything on this configuration. Oh, I'll show you the VHDL in a second. And this is an adder. So if I go here and I put 0, 0, 0, then we can change the adder. So if we go back to that source real quick, open up file location, we go to the 83020 VHDL, we can see they have the entire example of what they did to get this running. And so the LEDs, they just have this connection right here, where they say this bottom 6 of this thing, of this wire. And this wire is connected to their Opal Kelly host interface. Okay, host. But that's probably the work the front panel. And we don't have that's purely, if you buy it, you get access to their HDL, so I won't be able to show any of that HDL here on the stream, but if you do get the board, they have a lot of instructions for how to get this up and running. But that's all there is. And we can also open the XDC file, and it has all the pinout. So you see these pinouts, these are on the FPGA banks that aren't in the schematic, and it upsets me slightly. Oh, we have a clock here. Oh, and abuse that clock. And the LEDs. So we have the same thing for the counter, so we can go and load up the counter one real quick. Go ahead and close this one. So we're going to load up counters, and we're going to load up the counters XML. And if you notice, headphones, ground. If you can see that the LEDs are counting up, and somehow this is messing with my headphones. I don't know why my headphones are getting feedback from this. That is weird. So we can disable the counter like this, and then we can let it run. And we can reset it. Wow, why is this affecting my headphones? So if I hold down the reset, my headphones are going crazy. It's hilarious. Okay, for some reason, their driver software is affecting my headphones. That's funny. Let's exit out. That is hurting my ears. So no more of that. Ow. Okay, it's still doing it. Let's go ahead and just close this out. Maybe reopen it. Oh, is it still going to hurt my ears when it goes up? Okay, good. The front panel is no longer tagging my headphones. That's good. Okay, so we can go look at the HDL for the counter. Also, it's not that complicated. Do samples, counters, VHDL, counters. And this is just the HDL, and they just have the counters coming in here, and they're counting up the counters and connecting it to the LEDs right here. So really basic, really simple. And the reset is connected on that wire. That's about it for the counters. Now let's look up the more interesting ones right here. So we have pipe test. The pipe test, you'll need to get the API. So if we look at the APIs real quick, we have the supported APIs. And then for each of these, if we go to, I guess, lib for this one, x64, we have the OK panel front DDL, which is for the C++ example. So if we go to like the pipe test right here, it says you want to grab this executable and then put it in the same directory as the DLL and the bit file. So if we then go to this directory right here, and we do this by name, I have the RAM tester, the RAM test, and the OK front, the Opal Kelly front panel DLL. And if we open up here, I've already been playing around with this in my pipe test. Okay, so oh, we gotta turn off the front panel for this because only one controller can be on the device. So here we have a C++ example of doing a transfers over the USB. So we can see write speeds and the read speeds. And let's see, we can do a stress test. So we're reading around 300 megabits. We're writing about 100. I wonder if I put this into a higher speed port, would it change? Let's try that real quick. I'm going to change the port on my PC and see if that changes the speed. Give it a few seconds. Let's see. Did it find it? Okay, about the same read speeds, about the same. A little better on the write speeds. I should try USB-C to USB-C sometime. It looks like my camera died? Looks like my camera died. You guys are still watching. Let me try plugging this guy back in. I don't know. All this USB driver stuff is kind of messing with all my other USB drivers. I should have probably done this on another platform rather than the one I use. Try that. Okay, cool. We're good. So camera's back up. So we can do a stress test. Let's see if the stress test breaks my camera again. Stress test didn't break my camera. I wonder if all my other USB traffic is screwing this up, because I have a bunch of USB devices. I wonder if I cleaned off the USB devices, if this would run a lot better. Okay, so next we're going to transfer a whole we're going to do a whole gig and a whole gig back, right? I'm just doing a really large pattern of values over the pipe test, transferring a lot of data. Looks like we missed some frames there. Interesting. Okay, so that's about the speed. So and once again, there's VHDL and whatnot. We can look at that. So next, we're going to look at the decryption encryption core, which is using actually no, let's run to the RAM test. We're gonna do the RAM test real quick. So the RAM test is really basic. If I can find it. Did I not solve this one? Oh yeah, this just runs a lot of data over and over again. I'm not sure how many times it runs it. So this is writing to the DDR, writing back, and verifying everything is working. I don't know how many times it's going to do this. Well, we can look in the code real quick to see if they have go ahead up and open the code in Visual Studio so you guys can see what the RAM tester is doing. Okay. That's fine. So if we go to the RAM tester, right? How many times is this running? We go to main, the real main. Go to definition, the real main, num test. Okay, where is this defined? Go to definition, num test. So it's going to run it 10 times. Okay, cool. So we have the C++ that we can go through and look through, and this is cool because in Visual Studio, like, I can rebuild the solution and it works. Yay! I built the executable. So if you have Visual Studio, they provide projects and whatnot, so you can get up and running with their examples, manipulate them, throw stuff at them. It's really cool. I really like it. Opal Kelly is doing a great job. So we're gonna let it do a few more passes till it get to 10, and then we're gonna go ahead and do the other one. So while we're waiting for the DDR test to finish, we can talk about the de-encryption and encryption core. If we go back to right here, this is the de-encryption and encryption core under Opal Kelly. They have a little README, and it's like run it with E or D for encryption or decryption, give it a code, give it an input file and an output file, and it will encrypt files and decrypt files. And we'll do this with the C file or the C# file, and then we'll do this with the Python file for the decryption. So, okay, so if we go back to this file, we're going to delete our output text file and our test text file. Let's go back to our input text file and edit this. Hello world! This is a live stream on, or say about Opal Kelly XEM A320 or 3230, right? Yeah. Exclamation marks, enter. Okay, now we go back here. This finished at 10 memories. It all passed. I think there might be options, but that's about it. So let's go to the encryption core. Okay, so here we're going to use the encryption core to encrypt the input text file using this key, and it's going to output text. So let's go ahead and run it. Our encryption works. So now if we go back to this directory, we have an output text. We try to read this file. We have gobbledygook. Actually, can I open this in? My hex editor. I could open that in a hex editor. Oh, won't worry about that for now. And now let's go back here, and now we're going to decrypt using the Python version. So Python version decrypt to test.txt. And it worked. And if we go back here, we have this file that's just created a few moments ago. And okay, apparently the Python version and the Python version and the C version don't necessarily generate the same results. Interesting. Okay, let's try encrypting with the Python one, right? So we're going to encrypt the Python one, and we're going to decrypt the Python one. See what it looks like now. Reload. Okay, so there's a mismatch between the C# version and the Python version. Cool. Well, not my job to look into that, but we were able to do it that way. If we want to look at the Python, it's right here. Okay, Pi. No, that's not what we want. We want the tester Pi right here. And they're just initializing the device and have all these different configurations to get going and examples. It's really cool. I like it. I like it a lot. So those are kind of all the examples. They have a flash loader, which is more of a utility rather than an example. It's the same thing that's in the GUI. I don't really want to run through it right now, but it's there to be able to program the FPGA flash. We still have 30 minutes, but the next part may take a while. So those were Opal Kellys examples. I want to run through the Vivado board files. So the Vivado board files were actually added today. So we look at this. Today, this commit was done, and this added the Opal Kelly board to Xilinx's branch for 2021.2. I've had a few issues, but hopefully we got it running. Oh, we still have issues. We'll figure that out. We'll go debug that later. But let's show you how you set up a new board like this. Quick comment. The Artix UltraScale Plus is under the Kintex UltraScale directory in Vivado. You need to install Kintex UltraScale Plus part files to get this to work. And we're going to do a simple MicroBlaze DDR test with JTAG over UART. And I'm having issues with the DDR clock right now with the board files. We'll figure that out in a moment. But let's go ahead and create a new project. Maybe we'll play around with it. So let's do a new project. We'll do this. Is going to be number 3 of this project. So what we do is we go to boards. We hit the refresh button. This is going to clone or check out the recent commit, or just check out the branch for this version of Vivado. So we'll see how that goes. Hopefully this doesn't take too long, and we'll figure out how we can do the DDR. We do about the reset. It's taking a bit of time. So I think I'm going to try to set up the clocks manually rather than use the board settings. I think the board settings are screwing it up a little bit. I think that should be nice. Shouldn't take too long, I promise you. Other than that, we're pretty good. Okay, while we wait, let's go talk about future projects. So there's a lot more peripherals I would like to look at in this project. There's PMODs, PCIe, camera, Ethernet, some fun ones to look at. I also want to look at how to do internal JTAG debugging over USB-C. I've done this before over PCIe. I think I can do it over the USB-C interface. We can show how the ILA cores work with that. The MicroBlaze debug module works with that. We can do some BBRAM encryption examples. I would also like to do kind of a USB-C pipe to DMA AXI-bus connection where you memory map your AXI-bus to the USB-C device. It'd be fun to do it with Python. I would like to port the Linux on Linux repository for Vectorus 5 to this board. It's gonna be weird because there's gonna be portions that I want to be able to use the DDR or the USB, and the closeness of the USB driver and the openness of that repository is probably gonna make it a little bit difficult, but we'll play around with it. I would like to try to get Pink working on the host PC and basically connected to the Python connection for the for the Opal Kelly front panel, so we can do Pink-like rapid prototyping with the USB-C and the PC as the host. I also want to develop a USB-C 420 transceiver core, being a 20 gigabit core, and then maybe produce a PCB for that. Get this working with Vitus AI. Look at some crypto mining algorithms on this board. I'm just curious and more getting the algorithms working on an FPGA. Okay. Oh, why is this taking so long? Guys, tempted. I already have it. Okay, let's just close it, right? Close window. Okay, let's kill it. It'll start working as soon as I kill it. Task. Oh, did I get it to work? Oh, cool, we killed it. Ugh, takes too long. I wonder if because I updated it, do they have it? They don't have it yet for the patch. Oh, bugger. I upgraded my tool, so it may not be able to find it correctly. Oh well, we have it. We'll work with it. I think I'm too ahead. I'm broken everything. So we go vendors. Oh no, I broke it. Bugger. I broke the board files. Let's see if we can hack our way into this. Okay, time to figure out where they clone this file. Vivado. Data. Boards. Board schemes. Current. Board shop. Store. Let's go to the instructions, right? Go to the wiki and get this board store working. How to use the Xilinx board store. Okay, I think what we want to do is we want to be able to use a branch. How to test the pull request before merging. So we make a directory. Okay. Okay, so let's grab this code real quick. Because I broke it. I broke it bad. I updated Vivado and there's no patch for it. Oh well. We'll show you how to do this the hacky way. Hopefully that doesn't take too long. So what we're going to do is we're going to trick Vivado. We're going to set this property, and then we're going to refresh it. Okay. Hopefully it doesn't take too long to download. I upgraded my Vivado, and that screwed over the store. Actually, maybe we can just look at we could do get param. Try that. This is a set property. Let's do a get property. Right. Set property. We're gonna do a get property here. We'll remove that. Do we wanna get what's it? List properties. Here we go. Private repository. Yeah, let's do that. Get property. Remote repo branch, remote repo URL. Okay. No, that's right. That's right. So let's update. Let's refresh the catalog. Sorry. Taking a long time to download. Ugh. We may have to delay this. I'm gonna try for the next 15 minutes. The stream may get a little boring. But we'll see where it goes. We'll try to let this go and properly refresh. Kind of I'm curious to where they put this. See if we can find out where they put this data. Xilinx. Okay, data. Where is the board store? Thought it'd be in data. Is it up here? Can't be under parts, can it? Parts. Xilinx. I mean, we could just go, where is the KCO 105? Tell me. Ah, there we go. It's under Xhub. Open the directory. Ah, here we go. It's loading stuff. This is where they now have the board information. Boards. Is there anything that's updated? Commons boards, Xilinx boards, Xilinx. I wish this was more informative. I mean, this is taking forever. I wonder if it's just because we're having a large upload data rate right now. This is streaming. This could be the issue. Oh. Yeah. Did it achieve anything, or we are the stream killing this? The stream is killing this. Okay, remind me, I need better internet. Okay, so maybe that's where we're going to end today. We're having troubles connecting to the GitHub repository while I am streaming. So the best thing to do in this situation would be like, we're going to end the stream. I will fix this issue. I won't hit refresh next time during the stream because apparently the stream kills my internet connection. And this should be so much faster. And we can see where it goes from there. So tomorrow we'll go ahead and do the board files, but we'll go ahead, get the MicroBlaze working over JTAG, and then we'll start working on probably this internal JPEG thing because I just really want to get that working. Tomorrow, we may not stream tomorrow. We may have to wait the Wednesday. Okay, but join us as we look at these future projects. Thanks. I hope we can continue to look at this board. I plan to actually do a lot of my future development on this board because I just kind of really like the application of the Artix board. It's going to be the next set of hobby boards if we can find a affordable version of it. It's not very affordable at the moment. I hope to. I plan to look at seeing if I can develop a hobby board for this. Maybe release it on Crowd Supply. We'll see. If we get closer, you'll see a little bit more things about that. Vivado being Vivado. Well, it's also my internet connection. Sheesh, this should download way faster. Yes, but Vivado being slow.